Hello, welcome to Mr. T's Geometry videos. In this video we're going to study some theorems about quadrilaterals. Again, I'm not going to write formal proofs for each of these, and I encourage any viewer to go and either first try to prove them on their own, and then if you're not able to, go find my YouTube channel, and on my YouTube channel I will have proven each of these theorems on their own. The first thing we're going to look at are kites. Now, a kite is, if you remember, is a quadrilateral where consecutive sides are congruent. So in this case, AC is congruent to CB, and AD is congruent to BD. And so AC and CB are consecutive, BD and AD are consecutive. Now, one thing I am going to do when we talk about these theorems is I'm going to call line CD the major axis, or the major diagonal. And the reason we're going to call that the major diagonal is because it connects up the vertices between the consecutive sides. And usually when you draw in a kite, it's the longest diagonal. Now, not always. You can have a kite where that's not the longest diagonal, but most of the time when you see it, it is the longest diagonal. Okay, so our theorems are, first one says that the diagonals of a kite are perpendicular. And so whenever you draw on the diagonals of a kite, you know that you have congruent, you have 90-degree angles created by those two diagonals. Very powerful theorem. Another one says the major diagonal, remember in our picture it was CD, bisects the minor diagonal. And so it goes through the midpoint of that other diagonal that was drawn. And so we'll look at that in a second. And then finally, that major diagonal also bisects the angles as well. So when we look at our picture, what we learned, first we learned that AEC is a right angle because AB and CD are perpendicular. Then we learned that AE is congruent to EB because CD bisects or cuts in half AB. And then finally we learned that ACE is congruent to BCE, those two angles, because CD bisects those two angles. And the same thing's true about ADE and BDE. Now, why or how do you prove this? Well, it's actually a little bit tricky because of the way my picture looks. You might think that you want to prove that triangle ADE is congruent to triangle BDE, but that's not what you do. Instead, you do the big triangle, so essentially remove AB, that segment. It's very easy by side to show the two big triangles congruent. Then that by CPCTC shows that those two angles that I have marked on here are congruent. And then when you draw back in ABE, you can show that the two sets of little triangles are congruent, and that gives you the other pieces of information. So again, start with the big triangles and then do the small triangles. The next thing we're going to study are trapezoids. The first trapezoid theorem we're going to look at has to do with the base angles of this trapezoid. Remember, CD is parallel to AB. That's what it means to be a trapezoid. In this case, we're going to talk about an isosceles triangles, and our theorem says the base angles of an isosceles trapezoid are congruent, which means they're the same size. So again, in our picture, that means that A is congruent to B. Angle A is congruent to angle B, and angle C is congruent to angle D. Those are the base angles. There's actually two sets of them. To prove this, it's actually pretty simple. There's multiple ways you can do it. One of the ways to prove it is to draw in the diagonals. So you draw in AD and you draw in CB. And if you draw those diagonals in, you can prove two triangles are congruent using side angle side and some things that we know about parallel lines. Or what most people know about it is you can draw in the angle the altitude through C. So you're going to go up here to C, and you're going to draw in a bisector or altitude, which means a right angle to AB, and the same thing about D. Okay, now the next thing we want to study is we want to look at the diagonals of an isosceles trapezoid. And in the diagonals of an isosceles trapezoid, we find out that they are congruent to each other. So the diagonals of an isosceles trapezoid are congruent. So that means that AD is congruent to BC. And to show that, we know by the fact that it's isosceles that AC is congruent to BD. We just showed in the last theorem that angle ACD is congruent to BDC because those are base angles. And then we know that CD is congruent to itself. That proves those two triangles congruent, which then in turn proves that the diagonals, which are the long side in both those triangles, are also congruent. So it's a pretty easy thing to prove because we know using the definition of isosceles trapezoid and what we know about the angles of an isosceles trapezoid. All right, the last one about trapezoids is actually something that you should already know, but I just wanted to reiterate it. It's more of an idea. It's not really a theorem as much as it is just a concept, and that is, in a trapezoid, the angles between parallel sides are supplementary. And that's just because in any trapezoid, AB is congruent to CD, and so A and C are supplementary to each other. And that's, again, because A and C are considered consecutive interior angles for parallel lines. And same thing about B and D. So that's just really a review of parallel lines. All right, the last thing we're going to look at is a little bit different type of theorem, one that you maybe haven't heard before, and that has to do with the midpoints of any type of quadrilateral. So we take any type of quadrilateral, and we find out that the midpoints of the sides of a quadrilateral, so you take any quadrilateral you want, doesn't matter what it looks like, find the midpoints of all four sides. If you connect them, those connections form a parallelogram. So what that means in our picture is this is A, B, C, D is a random quadrilateral. We found the midpoints of that quadrilateral. E, H, G, and F are all midpoints. And then we know that now E, H, G, F is a parallelogram. The proof for this actually is best done as what's called a coordinate proof. And if you've not done coordinate proofs before, then again, go to my YouTube channel and find a video about coordinate proofs. Actually, this proof will be on there somewhere on the coordinate proofs. It's a very nice example of coordinate proofs. So anyway, those are our theorems about quadrilaterals. I encourage you, if you've gotten this far and you felt like I moved too fast, please hit rewind, hit pause when you get to that point, write down the theorems. But this is just a great video for you to use as review before a test or quiz or just a refresher before the SAT or something like that.